today. Let me start off with, I don't know, I have the alphabet still up here for a little bit longer. There's an honors pre-cal kid that hasn't taken his test yet. And it's just easier for me to leave it up until he does tomorrow in class. But if I was to give you something like this. Oh, this is a horrible marker. I haven't put any numbers in. This is what we would call a rectangular array of numbers. An organization where we have both rows and we have columns, right? If I was to ask you guys for the order, which some of you have already realized is totally coming up in the examples next, the order of this rectangular array, we call it a matrix. What size matrix would this be? Any ideas? 2 by 3? Those of you guys that found, and everybody should have because you were collaborating, turning in your group, someone should have a calculator, right? In your matrix menu, how do you put in a matrix? How do you get to matrix anyway? Second math, right? Which, second x to the negative 1. There you go. Second x to the negative 1, which is the matrix menu. And then you go over to what option? Edit. And then as soon as you hit like matrix A, right? What's the first question? Where's the cursor blinking? You know, it depends on your calculator and what you've put in it before, but it's a number and then an x and then a number, right? That's the size. So if you were to put in a 2 by 3, like a 2 by 4, if you go to Lowe's and you try to get a 2 by 4, it's the size, right, of the plank that you want. Same thing here, 2 by 3. Does it give you this size matrix to fill in? Okay. So when we're talking about order up here, and you guys see it down here, what comes first is the number of, well, we have rows and columns. So which one comes first, guys, if 2 is the first number? Rows. So we have rows first. And then we have columns second. And so a notation that you guys are going to see from time to time, you're not going to have to use it all the time, but it is going to be helpful every now and then, is a little lowercase a. I guess you could use B's or C's or D's also, but if you use a little lowercase letter, it could stand for an entry in a matrix, but there are 2 numbers down below. And it's not A11, A12, A13, it's A11, A12, A13, because M, the first number, stands for what row you're in. And the second number stands for what column you're in. So this is the entry in the nth row and the nth column. So does it make sense what I wrote up here? A11 is first row, first column. A12 is first row, second column. A13 is first row, third column, right? A21 is second row, first column. A22 is second row, second column. A23 is second row, third column. So this final little number is in the bottom right-hand corner is going to be the same thing as the order because you've gone through all the rows and all the columns. Now, once we eventually get to word problems and applications, etc., there will be different titles or different labels for the rows and the columns and what they mean or how they help organize information, yada, 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 but that's not for a while yet. So let's come back. If I was just to ask you then, oh, wait a minute, hold on, I totally skipped this. What's going on? Systems of equations. Subtraction? Subtraction. What's a better way for subtraction? Why did I put subtraction? Substitution. Sorry, guys, that's weird. 7.1, yeah, I don't know. I mean, subtraction's part of elimination, I suppose, but substitution, that's weird. Substitution, that was 7.1. Elimination, that was 7.2. Row echelon with back substitution was 7.3. And guess where we are now? Oh, that's not green because we haven't done it yet. That's new. 8.1. Wow. Rainbow effect. All right. Finally, we're back to blue. Here we go, 8.1. Yikes. 8.1. But anyway, hold on. Before we get to solving systems of equations with matrices, we're going through the basics. So what size is this little matrix right here? Yeah, it's just a 1 by 1. And more specifically, we could say that is A11, right? That looks like an absolute value of x, not what I intended. You guys heard me say it, right? 1 by 1. Okay, what's this guy?
1 by 4.
1 by 4. I could do A11, A12, A13, A14. Yeah? This guy's a little 2 by 2. And we could call him a square matrix because the rows and columns are the same. And this guy would be a 3 rows and 2 columns. 3 by 2. You could think it's an A11, A12, A21, A22, A31, A32, 3, 2. 3 rows, 2 columns. So the same way rows come first and then columns in the order, rows come first and then columns in the name of the entry. But all those had numbers in it. It wasn't that big a deal. So that's just how we talk about the size of a matrix. There are some special ones. Like, for instance, letter B, we could call him a row matrix because he only consisted of one singular row. Just like there could be row matrices, there could also be column matrices where there's only one column with however many rows. Square matrices are the guys that have the exact same number of rows as columns. So it's always going to be an m by n, 3 by 3, 4 by 4, 10 by 10, etc. And there's one last special one as far as having a special name on its own without being related to something else, the identity matrix. It's a square matrix with a main diagonal of 1s, and the rest of the elements are zeros. Elements or entries. We could also say entries as well. An example of this could be, I'm just going to do dot, 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 because this could keep going. Could keep going however big and however long and however far we want it to go. It just needs to be a square matrix. So I showed you a 3 by 3. It could have been a 4 by 4 and just go one extra one with the rest of those. It could be a 5 by 5, go an extra one with 0 zeros. A 6 by 6, etc. Now identity, that's an interesting word. We've seen that before in math. There's the additive identity to like numbers. We could actually say any real numbers, actually even imaginary numbers, to be honest, even real and imaginary. The additive identity would be 0, because any constant a plus 0 is equal to a, right? That's the additive identity. What's the multiplicative identity? A times 1 is equal to a. We could talk about like the multiplicative inverse. There's a multiplicative inverse times 1 over a. Whatever undoes and gets us down to 1. So there are different times that we've seen identity before. There's the additive identity. There's the multiplicative identity. And then there's the multiplicative inverse. Undoing a times by 1 over a. There's also an additive inverse. No, additive. What would undo the a with addition? Negative a, yeah. So additive inverse would undo the addition, and so you would get to 0. Multiplicative would undo the multiplication, you would get to 1. So lots of zeros and ones, but identity matrix. Now some of you might remember matrices in addition, and when we get to addition, the question is this an additive identity or a multiplicative? Right now I haven't told you. Right now we just know it's an identity. We'll have to see when we get there as far as operations on matrices, which I think is section 8.2, which identity it is. But for right now, well, I don't know. It's going to be one of these two. And maybe inverses are coming also. That's just a quick recap, though. Sorry, I didn't mean to totally go random on you guys. But we've seen inverses and identities in other things like numbers, and we're going to see them in matrices soon. But not yet, not today. Today, if we come back to the title of this section, it says Matrices and Systems of Equations. Our book says, let's start off with how to use matrices for systems of equations before we dig deeper into matrices themselves. So we know the basics, we know the size of a matrix, m rows, n columns. A few special names of matrices, but now we're going to talk about, okay, we've been doing a whole chapter of systems of equations. Chapter 7, substitution, elimination, row echelon back substitution. Partial fractions, needed systems of equations. Systems of inequalities, needed systems of, well, inequalities. And now they're saying, okay, let's lead into matrices with systems as well. Here we go. We have 8x minus 4y is equal to 7. 5x plus 2y is equal to 1. It's an easy one. I mean, it's not too bad, right? If we were doing this like last chapter style, I don't know, what would you guys think? Multiply the bottom by 2 and then put it all together? Yeah, I agree. But here's the dealio. I've chosen an easier example to show you the basic idea of how matrices can be used. Because I know that you guys can look at this one and be like, yeah, it's elimination, no big deal. I could solve it fast. But that's not the point. The point isn't for you as a human to look at a problem and analyze it and be like, I know how to solve it the quickest way. Because the problem is harder problems are coming. And we want a system that'll work. Now, that's kind of what we did with row echelon form and back substituting. Instead of looking at each individual problem as like, oh, it'd be really easy to get rid of the y's, get rid of the z's, get rid of this, get rid of that, do this, do that, and having to have a whole new system every single time a problem came up, we're like, no, every single time. Eliminate x's, eliminate y's, z equals done. Well, z equals back substitute done. We had a system and it worked every single time as long as you followed it. We'll see whether or not you guys totally followed it on your test, but there was a systematic approach. And we were kind of talking about computer programming just a little bit. Because if you're able to find a systematic approach that can work every time, well then maybe if you learned programming languages, you could tell a computer to do the systematic approach for you. And so I know a lot of you are looking at this and being like, multiply by 2, add, and we're done. And if you want, you can find the answer right now, and that's okay. I don't think that's totally bad. For us to have an idea of what the answer is, 8x minus 4y equals 7. 10x plus 4y equals 2. If you put those together pretty quickly, you get 18x is equal to 9. X is equal to 1/2. Once we have that, we could back substitute and say 8 times 1/2 minus 4y is equal to 7. That's going to be 4. We're going to subtract it to the other side. Negative 4y is equal to 3. I should say, yeah, positive 3. And y is equal to negative 3 over 4. Now hold on. Does anybody double check my math? 10 and 4. And that cancels. 18 and 9. Divide. Half. 4, 3, negative 3/4. We know what the answer is, but the problem that we were trying to answer wasn't necessarily the x or y, but how are matrices going to be helpful? So here's what's going on with matrices. We know what the answer is, 1/2 and negative 3/4. But you know what matrices can do? They can solve a lot more than a 2 by 2 or 2 variables, 2 equations. 2 variables, 2 equations. But it has 3 columns. We'll get to that. But 2 variables, 2 equations. Matrices can solve 3 variables, 3 equations, 4 variables, 4 equations, 5 variables, 5 equations, 10 variables, 10 equations. And it's because someone has programmed. Well, actually, there's a system behind how they work that's pretty easy to program into a calculator computer, which you guys have in front of you. But I don't just want to show you the operation and be like, yay, look, you can solve any system as long as z doesn't equal a from here on out. I would much rather you understand the programming behind it, because one day I'm hoping that you guys aren't just like these little number crunchers, like the computer can do it, how? Cool. The computer can do it, how? Cool. The computer can do it. How? Cool. But actually maybe the people behind the scenes being like, this is the problem that you need to solve and you need a computer to do it. Let's figure that out. So we're not going to go into all the different computer languages and how to program them today, but what we are going to do is at least take a little peek behind a program in your matrix math menu and how it works and what it's doing and why. So here's what we're going to do. We're going to take this matrix. Sorry, it's not a matrix yet. It's just a system of equations. We're going to make it into a matrix, taking the coefficients from the x column and the y column and the solution column. And we're going to put a solid line or a dashed line. You can do it either way. You can put a solid line or a dashed line either way. Technically, it is the row echelon form process or procedure, just not dealing with the actual systems, but dealing with the numeric coefficients instead. It's kind of simplifying the process from last chapter 7.3. So it's not all going to feel new. But I did put a couple hints here on the side. Let me go and zoom in. I did put a couple hints here on the side as far as my approach and what we're going to do. We're going to try to establish the 1 and then get zeros, working by columns. So if you guys notice, there are 1, 2, 3 different columns. I have alluded to the fact that this third column is kind of off on his own. He is the other side of the equation. I'm not showing you all the math right now as to why. We're only really going to be working with the left side and not the right side. When we talk about matrix multiplication and identities and inverses, I can kind of show you exactly why. But for right now, I'm going to have you guys go on faith just a little bit. We are going to work by columns in this side of the matrix and just see what happens over there on that side. So working by columns, we're going to first choose column number 1. And choosing column number 1, we're going to establish the 1 by multiplying by the reciprocal. Now you might not know, because there's only 2 entries in column 1, where we want the 1. But if you guys noticed a second ago, I was talking about a very special matrix called the identity matrix. And he's actually our goal when we're solving systems. He's our goal. What we want to get is actually an identity matrix with, well, we're not exactly sure what's going to be on the other side. But our goal is to get the identity matrix. So a leading 1 on the top of the first column, a leading 1 in the second entry of the second column, and the third entry of the third column, etc., etc., etc. So right now, I want a 1, but I have a what in that first column? I have an 8. Now, multiply by the reciprocal. What's the reciprocal of 8 over 1? 1 over 8. So as we come down in this next step, we're going to actually be making matrices and kind of changing and adapting them every time as we go. I'm going to tell myself, and you're going to tell yourselves, what you're doing to change it. I'm taking, remember how we would call the first equation R1, second equation R2, etc.? I'm going to take R1, and just like we had to do with equations, what we do to 1, we do to all as far as multiplying or dividing. We're going to have to do that here as well, but we're just doing it to the numeric values. So I'm going to multiply by the reciprocal. I want my 1. And guys, do you see what happens if I do 8 times 1/8? I get 1. But what's negative 4 over 8? What's 7 over 8? Well, and if you guys noticed, I just got my 1. Now I'm going to go ahead and rewrite row 2 because my goal, first of all, was just to get my 1, and I have it. But after I get my 1, working by columns, so I have to finish column 1 before I move to column 2. Every time I'm at a column, I get my 1, and then I get my zeros. Now I say zeros because this could be a huge matrix. But this one, there's only one other entry, and so what do I want that other entry to be? 0. But how do I get it? Multiply the row with the 1. Which row has the 1 right now? the new row 1. Multiply the row with 1 by the opposite number. What's the opposite of 5? Negative 5. So what we're going to do is actually keep row 1 the same, because he has his 1 just like I want him to have. I'm trying to get my zeros, which is in row 2. So let's do literally what it says. Multiply the row with the 1, which is row 1, times the opposite number, times negative 5, and add. Add to what? The row I'm trying to get to. So if I do negative 5 times R1 plus R2, yeah, because check it. Negative 5 times 1 plus 5 is 0. The dilemma is to keep everything legal, I can't just do it to one little baby piece of these all go back to equations. I have to do it to everybody. Like with elimination, if you would double an equation, you would double every single piece. So same thing here. I'm going to multiply everybody by negative 5. Now some of you are like, whoa, there's a lot of mental math going on. For some of you. Joe? So therefore, if some of you guys are like, I got the mental math. Can you finish the row for me? That would be great. If some of you are like, there's a lot going on. What you can do off to the side is you can actually, instead of having to try to do it all in your head to fill in, you can come over here and an in-between step you can actually do, okay, I want to multiply this entire thing by negative 5. And then you could go ahead and come over here to the side and you could say, all right, so I'm going to have negative 5 and 5 halves and negative 35 eighths. And I'm going to add that to, that's my negative 5 R1. I'm going to add that to 5, 2, 1. So some people were maybe doing this in their head of taking each one times negative 5 plus times negative 5 plus times negative 5 plus. But some of us, that's a little too much math, a little too much mental math. You can actually take that entire row like you would do with elimination times negative 5. And so I multiplied 1 times negative 5, negative 1/2 times negative 5, and 7/8 times negative 5. And then we add down, which that will be 0 like we got. But this one, you have a little more space to say, wait a minute, I don't know what 2 and 5 halves is. Now some mental mathers would be like 4 halves and 5 halves is 9 halves, no big deal. Or 2 1/2 and 2 is 4 1/2, no big deal. But for the rest of us, we could go ahead and get a little common denominator right here and do 5 halves plus 2 times 2 over 2 is 4 halves and say, okay, 9 halves, got it. For some mental mathers, negative 35 eighths and 1 wouldn't have been a big deal, but for others, no, I need a space to multiply by 8 over 8. And so I can do negative 35 eighths plus 8 over 8. If I can make that an 8, it's going to be negative 27 eighths. Especially with fractions. Some of you guys are going to be just fine doing the mental math, but others of you, it might be helpful to kind of do the math off to the side. But once again, what we were doing was taking everything in the new R1, once we transformed it, multiplying by negative 5 and adding to the corresponding entry in row 2. So positive 5 halves and 4 halves, which is 2, is 9 halves. And then negative 35 eighths plus 8 eighths is negative 27 eighths, whether you do the math off to the side or whether you do it mental math style. Row 1, no, we're not working by rows. We're working by columns. Column 1, done. So where are we going to go now? Column 2. What's the first step? Hold on. First step, get the 1 and then get the zeros. Okay, so where should my 1 go if I want this to look like an identity matrix? Right there. What am I going to do? Well, what do your notes say? I want this guy to become a 1, so I'm actually going to keep row 1 because he's not changing in this step. He's not changing in this step. Row 2 is changing. What does the clue say? Multiply by the, oh, so let's multiply row 2 by 2 over 9. Now some of you are like, oh, this is going to be disgusting. But wait, what's 2/9 times 0? 0. Oh, What's 2/9 times 9/2?
1.
I got him. There's my 1. Got to do it to everything. What's 2/9 times 27 now? I know, some of you mental mathers are less mental mathers than others. So you could totally do -27/8. Good job, Joe. Wasn't talking to you, bud. -27/8 times 2/9. For my non-mental mathers, you can come off to the side and actually do, okay, he needs to get multiplied by him, and then you could do your little. But was Joe right? Yes, he just did it the mental math way. I could too. But I'm showing some of you guys who are like, yeah, the number thing doesn't happen in my head so fast. Okay, it's better to be right than to be quick. It's better to be right than to be quick. But do we have our 1? Yes. So now we're going to get our zeros in the column. I only have 1 0 to get, and it's just him. Now, technically, if we were just going to row echelon form, we could stop. And some of you might not realize how we could stop, but we could stop. I'm going to go off to the side. Don't worry about writing this. Let me just show you what I'm talking about. Row echelon form. Do you guys remember what row echelon form was when it came to equations? Didn't in row echelon form, didn't we just need an x, a y, and then a y? By doing this, we actually just got to row echelon form with a 1x and a 1y. And if this was an XYZ system and we had gotten a 1, 1, 1 and zeros only below, not above, we would actually have row echelon form. Row echelon form says, hey, you already got to one answer. As soon as I have a 1 with a number, I already have a variable. Did I write something wrong, Joe? Okay, so hold on and pause. So y equals -3/4, and then we could go ahead and back substitute, because technically row echelon form just says get leading coefficients of 1s with zeros everywhere else. But it didn't necessarily make sense to you before when I said that. I would just say 1x, a 1y, a 1z, and everything else needs to be gone. But in a matrix, what that's going to look like is leading diagonal of 1s, 1x, 1y, 1z, 1 a, b, c, d, e, f, g, I don't know, whoever else you have, and zeros before, because that way we're whittling down one variable every time. But in this one, we could finish solving it. We could go ahead and say x minus 1/2 times -3/4 equals 7/8. And we could have x plus 3/8 equals 7/8. X equals 7 minus 3 is 4/8, which is 1/2, which would match up with what we already know the answer to be. Right? And that would be following row echelon form, Gaussian elimination, as far as getting to a place where we could back substitute and be done. However, there is another way of proceeding without back substituting, and that says, technically, reduce it further. Don't just go to row echelon form. Now hold on, in your matrices, because you guys were playing with your calculator a second ago, right? Can you guys go ahead and edit matrix A to be this matrix that I gave you at the very, very top? 8, -4, 7, 5, 2, 1. 8, -4, 7, 5, 2, 1. It's going to be a 2 by 3, right? So you have to go matrix, you have to go edit matrix A to be a 2 by 3, and put in the very, very top, 8, -4, 7, 5, 2, 1. Now I want you to second quit, get out of there. Get back to the home screen, and from the home screen, go back to your matrix menu, but go to math this time. Go back to your matrix menu, but go to math. Can you guys go find me REF, row echelon form? REF, row echelon form. Hit that one. But you have to tell your calculator which matrix, so then go ahead and go back to matrix and choose A's name. So REF and choose A's name. REF is second matrix, math, number, what is it, 8, 9? A, letter A, that's awkward. REF, enter. and then go back to your matrix, second math, and then hit enter because it should be the name A. And then enter. REF of name A. What'd you guys get? Talk it out in your groups really quickly. Go down to REF A, and then go to your, oh, sorry. Does it match up with what mine shows? No, mine are decimals. That's okay. Hit the math button. Math button, go to fractions. Hit math, frac. Math, enter. And then enter. Ooh, look, nice little fractions. However, did that finish the problem for you? No. Why? Well, because it gets you to back substituting, but guess what we could have done if we had just finished our column? We could have kept this guy because we didn't mind him. He had his 1 like he was supposed to, but we needed him to get a 0, right? To get a 0, we would multiply whatever row has the 1, which is row 2, by the opposite, which is 1/2. Add it to the row we're getting to. 1/2, I'm going to do mental math. Lo siento, all those that don't like mental math. 1/2 times 0 is 0, plus 1 is 1. 1/2 times 1 minus 1/2 is 0. 1/2 times negative 3/4 is negative 3/8 plus 7/8 is 4/8. If I had just finished, can you guys do the exact same thing? Pause, but go RREF. Reduced row echelon form. Do the exact same thing, but the option right below RREF. Reduced row echelon form. Enter. And what does it give you? The identity matrix, if possible, and the answers. Dun, 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 dun. Tomorrow we'll see, what do you do with a 3x3, a 4x4, a 5x5? We could just do this all day long. Yeah, we could. Bye, guys. See you later. Toodles. Good job.